So model specific featurization technique. Now let's try to understand this technique through an example. Suppose this is the first example. So let's try to understand this type of concept through a various type of examples. Um, Suppose we have some features. We have some features F1, and we know somehow we know it's the power law. It follows the power law distribution. It's follow the power law distribution. Somehow do we know it? But we want to apply the logistic regressions onto it. How will we do this job? Suppose we want to apply the logistic regressions onto it. And we have already know that. We have already in logistic regression series, we have already know the in logistic regressions is another kind of it things called the Gaussian Nyquist. Means it follows the Gaussian distributions. It's another language, it's called the Gaussian Nyquist algorithm. Okay. So if these things, since we know the internal features of the logistic regressions follows the Gaussian distributions, so that somehow we have to convert these features, F1 features in logistic distributions. Then we can easily apply these logistic regressions onto it features. So since we know that, so the features of the logistic regressions are Gaussian distributed. So we know its features are Gaussian distributed. Since we know it, then somehow we have to convert these features F1 into the logistic regression. So how are we doing this job? Because we have know to convert some power law distributions into a Gaussian distributions, we have applied the Box-Cox transformation. Then it will be converted into somehow like Gaussian distribution. If we convert it in, then we can easily apply onto it the logistic logistic regressions. We can easily apply onto it the logistic regressions. Okay, that's the simple thing. Okay, means it's depend on the model to model. In which situations which kind of model we want to apply onto it. These things we have to know. Means this kind of idea we have know by simple seeing the data set, by simple and you have the knowledge of the particular domains. That's kind of thing we need. Okay, so this is the one example. Let's try to understand through another example. Example 2. Let's try it. Suppose let we have three features F1, F2, F3. We have three features and corresponding output of these features are the real number from the real number set of real numbers. And from some domain, from some specific problem, from some specific tasks. For such specific tasks, we have some domain knowledge. From the domain knowledge, from some specific domain knowledge, we have know somehow these y means the dependent variable, these output are related to the like that, like this way it is related f1 minus f2 plus 2f3. It is somehow related with this feature. Okay, so by simple using the concept of the domain knowledge, we have somehow know this kind of interactions they are have. Okay, these things are called the we have already known. These things are called the simple linear combinations of the FIs. These things are called the linear combination of FIs. These things are called linear combinations. So since we know the interactions between the features are linearly related, though so we can easily apply onto it the linear model. We can easily apply into it the linear models. So if you remember the linear model like linear regression, like that, like linear regressions we have applied. Now just see it. Here we have some weighted for this. Here weight. So if you just think W1 is weight for the features 1, W2 is weight for the features 2, W3 is weight for the features 3. So what will be the value of the W1 here? So value of the W1 here is 1. What will be the value of the W2 here? Value of the W2 is equals to minus 1. And similarly W3 is equals to plus 2. These are the weight values. By simply using this concept we can also. So means it's depend on the domain knowledge, expert interactions. Means to build machine learning models, actually it's matter on the interaction to interactions. If you have some machine learning algorithm knowledge, domain expert that have the simple specific domain knowledge. So if you interact these things, then we can easily build machine learning model. So, so let's try to understand through another example. Let's another example 3. So this example 3, suppose we have some specific problem. Suppose we have some specific problem. We have to make some model. We have to make some models and predict some y. This y are actually depend on the interaction between these two features of some data set. So interaction, these y are depend on the interactions between interactions of two features f1 and f2. Let for understanding purposes. And this interaction, this interaction concept we got from some specific domain knowledge. From some domain knowledge we got this thing. We got this thing. We got this idea. So suppose let's in our previous video we have taken the examples to predict the gender. Predict the gender. By using the features of the height and weight. We have seen these things. So if we have this kind of interactions between the features, this thing like to predict the gender. So in such scenario, we know these interactions are related to the logical operator. Okay, so in such scenario, we have applied onto these tasks, we have applied the tree-based algorithm. Tree-based algorithm. If you remember, the tree-based algorithms is like decision tree, random forest, or it may be gradient boosted decision tree. We have already known these things. It depends on the problem to problem. If we somehow using the one or domain knowledge, if we somehow we have find that there have these two features are interacted by using this logical operator, then we can easily on this specific task we can easily apply the tree based algorithms to uh, get such kind of better output. Okay, also if we apply instead of using the tree based, if we apply for this kind of interaction, if we apply some linear model like logistic regressions, linear SVM, like you can apply, then you may not get some kind of right answer. Okay, so this it depends on the problem to problem, knowledge to knowledge. Now let's try to understand through another example. Okay, suppose let's the back of word. We have some text data, and we want to convert this text data into some vectors, numerical vectors. We have no and these the simple things we have applied onto the back of word features transformations. If we apply the back of word onto it, then this text data is converted into a numerical data. Numerical data. When we learn the deep learning chapter, we will then deeply see in how deep the back of what is internally work. But let we have some text data, and using this back of what we have converted this text data into numerical data. Okay, and we have know that by using this text data, sometimes it's a very high dimensional spaces. We require for a text data, we require very high dimensional. We require the very high dimensional space. Okay, if these things happen, if these things are in, and we have also numerical data, and also it's come from the very high dimensional space to separate these two different outputs, we need some hyperplanes. So to separate it, this hyperplane, we need hyper. To separate this data, we need the hyperplane. Okay, hyperplanes to separate it from positive to negative. So I'm talking about like that. This kind of if we this hyperplane we need. And how we do this simple thing by to find the hyperplanes, right hyperplanes. We know there are various kind of models. So it could be linear SVM, it could be logistic regression, it could be linear regression, like that. It's depend to problem to problem. It's this kind of idea we need. So for high dimensional spaces, we needed hyperplane. So based on the hyperplane, we need find this hyperplane. We need this kind of models to separate the data from positive to negative. Okay. Sometimes for to find this for very high dimensional data, sometimes we will when we discuss the case study, we will see sometimes the decision tree, the random forest algorithms to helps us to find this data. But it's sometimes it's not always to find a better way. Okay, so typically, not typically, in general, generally, the decision tree based means tree based algorithm may not work well to handle this. You handle these high dimensional spaces. Okay, so in such scenario, we need some kind. I mean, it's depend on the problem to problems. So when we discuss the case study, then you will see how these things are applicable. Just the motto of this video is just to get the idea of what kind of featurations actually need to build a real world. Okay.